All right, here's the problem. So, okay, what we want to know is, so let's say there's a bunch of charges floating around in this room. Okay. What we want to know is, what is the electric field at all locations? Okay, everywhere in the room. Yeah. So for instance, this charge will, let's say we'll find the electric field at this point. This charge will produce an electric field in this direction. We'll call him Q2. This charge will produce an electric field in this direction. Yeah. Q3, there's E3 and E4. Okay. So the net electric field at this point is what? It's the sum of those four vectors. Okay. So you found the electric field at that point. Now you want to find the electric field at this point. You do the same thing. Then the electric field at this point. Before long, you'd be tired. Okay. And this is just 4 charges. What if we throw in a whole bunch more? That becomes almost an impossible task. All right, what Mr. Gauss does is he will let you calculate the electric field everywhere for very symmetric charge distributions. So let's say it doesn't matter how many charges you have. Let's say you have them all lined up evenly. Okay, and then, so in this case, okay, so let's say this is an infinitely long chain of charges. Okay, so for instance, here's an infinitely long chain of charges. What do you think the electric field is at this point? Which way will it point? Will it point up, down, away? Yeah, so intuitively you knew this. It's not going to point like that. It's not going to point like this. It's going to point like that. Okay. So for symmetric charge distributions, you can use Gauss's law to calculate the electric field. And this electric field will be, you'll see in a second, is E lambda 2k lambda divided by R. Okay. Lambda is the charge per unit length. Okay. So Gauss's law will allow you to calculate that. See, you had an infinite number of charges, and you calculated the electric field at this point without having to add up an infinite number of vectors. Okay. So that's one of the things Gauss's law does. Okay. It allows you to calculate electric fields for symmetric charge distributions. All right, so let's do this. There's a bit of terminology that you have to understand before we introduce this law. So Gauss's law is convenient for calculating electric fields of highly symmetric charge distributions. Okay. So this is a symmetric charge distribution. This is not a symmetric charge distribution. Okay, if that thread is all. Yep. And oftentimes we'll be dealing with, so when you deal with parallel plate capacitors, so we'll evenly smear that wall with charge and smear this wall with charge. Okay, so those will be symmetric charge distributions. All right. Gauss's law relates electric fields at points on a closed Gaussian surface. You'll understand this in a little bit, to the net charge enclosed within the surface. Okay, so that's what Gauss's law does. All right, Now, before we understand Gauss's law, like I said, we need to understand a bit of terminology. Okay. So first, we'll talk about material flux. So imagine that this is a river, and you have a ring here. Okay. And you ask the question, how many gallons of water are flowing per second through this ring? Okay. So how many gallons of water are flowing through this ring? The answer is the rate of flow is the velocity of the river times the area. Okay. Now let me make the ring go sideways like this. How many gallons of water are flowing through the ring now? I'm sorry? 0. Okay. So it seems like, okay, how about now? How about here? Is more water flowing through this ring or this ring? I'm sorry?
Same area.
Well, it was the same area.
It changes the shape of it, so.
No. I didn't change the shape. It's a rigid, but when I held it like this, okay, so.
Well, I'm saying like the shape of the area changes, so as you turn it, it will actually have less surface area.
Yeah, so if the river is flowing like this, the water flowing is A times V. Now the water flowing through this ring is 0. So it depends on the orientation. Okay. So to give you the material flux, what we'll define is an area vector. And the area vector is perpendicular to the area. The magnitude of the area vector is just the area of this surface. Okay. Now the flux through this, and you'll see in a second why we define this. The flux through this is, see, the component of the area perpendicular to the flow is A, this is theta, is A cosine theta. Okay, so that's the area that's relevant, the area that's perpendicular to the flow. So the flow rate is VA cosine theta. Okay, do you guys, is this formula familiar? If you look at the dot product of two vectors, it's A, B cosine theta. Magnitude of A times magnitude of B times cosine of the angle between them. Okay, so that's why we define the area vector. This is the velocity vector. So the material flux is given by the area vector dotted with the velocity vector. Okay, and when the area vector is perpendicular to the velocity vector, the material flux through that was 0. Cosine of 90 is 0. Okay. All right. So we'll similarly define electric flux. Okay. Again, we are building on the terminologies so we can understand Gauss's law. Okay. So let's say there's an electric field in this room, and the electric field is a vector field. So at every location you draw a vector, and the density of lines tells you what is the strength of the electric field at a given location. So that's how you represent it. Okay, because you can't draw vectors at every location, so it'll get too crowded. Okay, so here's a way of doing it. Now the electric flux you can think of as how many lines are threading this area. Okay, so again, so it would be just the electric field strength at that location times the area. Yeah, that's how we define electric flux. Okay, now in this case, if you draw the area parallel to the field lines, the electric flux here is 0. Okay, so again, we will define the area vector, and the flux will be defined exactly like material flux, E dot A. So there's the electric field vector, and there's the area vector. So the electric flux through this surface is E dot A. And that tells you the number of lines threading that. And if the angle between the two is 90 degrees, the electric flux will be 0. Okay? All right, what we'll be interested in is the following. Let's say there's a whole electric field in this room. Okay? What we want is, here's an enclosed surface. Okay, any enclosed surface. You could take your water bottle. Okay? And what you want to do is find the net electric flux through this enclosed surface. Okay, if a field line is going out of the surface, you count it as positive, and if a field line is going in, that's negative. Okay. So if there are 100 field lines going out of the surface and 102 field lines going into the surface, what is the net flux? -2. If 100 field lines are going out and 100 are going in, the net 0. Okay, so that's the rule. Okay. So for instance, here's a uniform electric field, and if you have a cube like this, there'll be equal number of lines coming out through this surface, but an equal number of lines going through this surface. So the flux through this surface would be 0. In fact, if the electric field is uniform, what does that mean? That is, the magnitude and direction of the field is the same everywhere in this location. So if the field is uniform, you can draw any surface, and the flux through that surface will be 0. For every line coming out of the surface, there's a line going in. Do you guys understand that? All right. So we want to calculate the flux through a surface. Okay. Now you guys are all calculus experts. If you want to calculate the flux through a surface, what you do is you break it up into little pieces. Calculate the flux through this piece. Okay. There's the electric field at that piece, and there's the area vector. Okay. E dot A. So E dot delta A. And if you want the flux through that entire surface, you just take the sum over all those little areas. Okay? And of course, if you want a very accurate result, what you want is to make that area smaller and smaller. So in the limit delta A going to 0. So that becomes a surface integral. Yep. So here's what you would do. So for instance, if you had a surface like this, EDA. Okay, so let's say this is not a closed surface, and you would add up all the fluxes through these areas. Okay, so for instance, here in this room, there was an electric field, let's say, and you wanted to calculate the flux through this surface. Okay, you would do this integral over the surface. All right. And of course, if this is an enclosed surface, then that's a surface integral. For a closed surface, you write a little circle indicating that's a closed surface. Okay? And so this is the surface integral you do. Okay. This is a positive flux, and this is a negative flux. And this is a 0 flux to that area. Okay. That area contributes 0. This area contributes positive flux, and this area contributes negative flux. All right, so for an enclosed surface, you calculate this surface integral. If this comes out positive, what does that mean? I'm sorry? That's right. So you have more lines going out than coming in. And if it's 0, that's right. And if it's negative, there are more lines going in and out. All right, so now you will be able to figure out Gauss's law. All right, so here's a positive charge. How are the electric fields look like around a positive charge? Okay, let me draw a closed surface. What will the flux be, positive, negative, or zero?
Based off of that image.
Mm-hmm. Positive. How about for this surface?
When they're still going out, right?
Yeah, so tell me, I don't know. Positive. How about for this surface?
Would you need to change where you're measuring, or do you just count? Is it 0?
Very good. For every line coming in, see, every line coming in is going out.
So it doesn't even have to have the particle in the
Right.
surface area.
So I'm just showing you the various situations. Mhm. How about for this surface? Negative. Hmm? 0. For every line coming in, there's one going out. That's what Mr. Gauss says. The flux through an enclosed surface is related to the charge inside. If there's no charge inside a closed surface, then the flux through that surface is 0. If the flux is negative through that surface, there's a negative charge inside the surface. If the flux is positive, then there's a positive charge inside the surface. Okay? Now, this is not a trivial statement. Mr. Gauss was one of the top, smartest mathematicians of all time. So, okay? So that's Gauss's law. Okay? So, for instance, in a uniform electric field, you saw that any enclosed surface, the flux will be 0. This is showing you a calculation for a cube. The flux through this, since the lines are going out, that's positive. The flux through this surface is negative, and the flux through all those 4 side surfaces are 0. So the net flux through that enclosure is 0. Mr. Gauss says the flux through an enclosed surface, you can draw any imaginary surface, is equal to charge inside divided by epsilon naught. So if the charge is positive, the flux is positive through that surface. Yeah. If the charge inside is negative, the flux through that surface will be negative. Okay. So for instance, what is the flux through this surface? There's no charge inside, so it'll be 0. For every line going in, there's a line coming out. What is the flux through this surface? There's a negative charge. You see the flux is negative through that surface. There's a positive charge here. Flux is positive. So the flux through this surface is positive. What is the flux through this surface? The total charge is 0. It'll be 0. Okay. And that is Gauss's law. All right, so it is relating the electric field on the boundary to what is inside the boundary. This is what's inside the boundary. All right, that's Gauss's law. Okay, so you can use that to calculate the electric fields in symmetric situations. And I might do one derivation, but I will I'll state a whole bunch of results for you guys. Okay. So this was Coulomb's law. It gave you the electric field from a point charge at a distance r. Okay. And I'll show you the derivation of that. All right, so let's go to okay. So again, Mr. Gauss allows you to calculate the electric field in only very symmetric situations. Okay. Now what we'll do is we'll derive. So really we're sort of using a hammer to kill a fly here. We're going to calculate the electric field due to this guy at a distance r from a point charge. Here is the point charge Q. Okay, so again, let's say this is the point charge. So this is a positive charge. If you were to guess, the electric field would point away from the charge. From this guy, away, like that. And at equal distances, you would think that the magnitude would be equal. Okay, so there, what you do is you draw a sphere centered at that point, and from symmetry arguments, the electric field is pointing radially outwards and has the same magnitude. We don't know what the magnitude is. All right, we're going to calculate the flux, which is the surface integral. This surface integral. Okay, so we've drawn a little area there, and there's the area. Again, these are all complicated integrals, but we are doing them in very simple cases. E and area are pointing in the same direction, so it's just the magnitude of E times dA. But E is constant everywhere, so you can pull it out. But what is the sum of all these little areas? It's the area of a surface area of a sphere, yeah? Which is E times 4 pi r squared. Okay. And Mr. Gauss tells you that that is equal to the charge inside, which is Q divided by epsilon naught. So E times 4 pi r squared equal to Q over epsilon naught. And so that gives you E equal to Q over 4 pi epsilon naught divided by r squared. And this is Coulomb's law. 1 over that is K, Q over r squared. And that's the electric field. So that's, using Gauss's law, we derive Coulomb's law. Yep. And that was possible because this charge, even though this was a single charge, it was a symmetric situation. Okay. So the electric field around a point charge at a distance r, the magnitude of the electric field is given by that. KQ over r squared. Okay, what this shows you is, again, now I'm going to state a whole bunch of results. Okay, so let's say you take a styrofoam ball and evenly smear this with charge. Okay, so let's say you evenly smear this throughout with positive charge. Okay. And Q is the total charge, and the charge density would be Q divided by, and the radius of this sphere is that, so the charge density would be charge divided by the volume, okay, of the sphere. So the charge density is charge divided by that. Okay, so what Mr. Gauss can show you is the electric field at the center of the sphere is 0. Okay. And as you come out of the center, as you go further and further, the electric field is linearly increasing. At the surface, the electric field is the greatest. Okay. And once you get out of the surface, the further out you are, the electric field for R greater than A, the electric field is KQ by R squared. As if this has become a point charge, it's behaving like a point charge. So once you're outside the sphere, the electric field at this point is the same as that of a point charge. All right, so the net effect is the following. Okay. So if there is a sphere and if this is only if the charge is uniformly distributed, okay, when you are here, the electric field is, you're affected only by these guys. These guys, the outside guys, do not affect you. Okay? And if you look at your old notes, chapter 13 notes from gravity, you'll see the same. The acceleration due to gravity at the center of the Earth is 0. It'll be maximum 9.8 meters per second square on the surface. And then when you go out, you go further away, then it falls off as 1 over R squared. R being the distance like that. Okay, so it's exactly the same. Okay, so here is what Mr. Gauss will say. So now if you have a infinite sheet of charge and the charge is uniformly distributed. So let's say you take a sheet of paper and the sheet is infinite and you're going to spray it evenly with charge. And what Mr. Gauss is saying, so if the charge is positive, the electric field will point away from the surface. And the magnitude of the electric field is sigma. Sigma is the charge per unit area divided by 2 epsilon naught. Okay. What I'll do is I'll derive this briefly, just so you have seen one derivation, and then we'll talk about something neat about this formula. All right, so let's say you have this infinite sheet, and let's say you're here. What would be your guess? And again, the sheet is flat. So all these arguments wouldn't work if there was kinks to the sheet. Okay. All right, from the symmetry of the situation, you know that the electric field cannot be like this, like that. It has to point perpendicularly away from the sheet. Okay. So what we'll do is we'll draw a Gaussian surface like this, just a cylinder. It's a cylinder, and the sheet is in the middle of the cylinder. Yeah, well, it doesn't have to be in the middle of the cylinder. The electric field on the other side is pointing away. The electric field on this side is pointing here. So what we're going to do is calculate the flux, and that'll equal the charge inside divided by epsilon naught. This is Gauss's law. Okay. These side surfaces do not contribute anything to the flux because the electric field is parallel to the area. Okay. So this guy, the electric field is E times, the flux through this surface is E times A. The electric flux through that surface, the surface on the other side, is also E times A. And that should equal the charge inside, and that's the area. So per unit area, the charge is sigma. So the charge inside is sigma times area divided by epsilon. Okay. So you see, what we have shown you in 2 seconds, we showed you how to calculate the electric field due to this infinite number of charges. Yeah. That was only when there's this, the charge are distributed on a flat sheet, infinitely flat sheet. Soon as you put a kink on the sheet, that none of your arguments are valid. Okay? So the charges have to be very symmetric. Now here's the neat thing about it. Okay, again, how large is this sheet? Infinite. Okay. So here's this infinite sheet. The electric field here is sigma by 2 epsilon naught. What's the electric field here? What's the electric field in New York? What is the electric field in the next galaxy? It's sigma by 2 epsilon naught in this half of the universe, sigma by 2 epsilon naught on this half of the universe. Okay. So you see, it's a constant in the entire universe. Okay. It's pointing in this direction in this half of the universe, pointing in that direction in that half of the universe. Okay, so similarly, you can show that if you have a infinitely long, uniformly charged line charge, then the electric field is 2k times lambda divided by r. Lambda is the charge per unit length, okay? And r is how far you are from the line charge. Okay, so again, we are showing you the electric fields of infinite number of charges, and Gauss's law allows you to calculate these electric fields very easily. So this is a cylindrical symmetry. Yeah. All right, now I'll just state a bunch of facts for you guys. Let's see. Okay. So, if you have a conductor, what is a conductor? Right. So most metals, they have a whole bunch of free electrons. Okay, so this is a conductor. So let's say this is a slab of copper. Okay. And let's say in this room, okay, so in this room, you had a uniform electric field like this. And in a couple of chapters, you'll learn how to create this uniform electric field. To create this uniform electric field, on the left wall, smear that left wall uniformly with positive charges, and the right wall with negative charges. And you'll get a uniform electric field like this. Okay? And then you go buy a slab of copper and place it like this. What do you see here? So what this diagram is showing you is there's no electric field inside the copper slab. All that electric field got kicked out. Okay. So, oops. So you put a slab of copper and all this electric field will get kicked out. What happens is, as soon as you put a slab of copper, the electric field here will move the free charges. Okay, so if there was an electric field like that, all the electrons will move here. The electrons moved here. This left a positive charge on this surface, which created a electric field of its own inside like that, which canceled the existing field, the external field. And all this happens very, very fast. Okay? So in equilibrium, inside a metal, okay, that's in static equilibrium, the electric field is 0. So if there's an external electric field, the charges on the conductor will rearrange themselves such that the electric field inside a conductor is 0. Okay? So if you had let's say you smear that wall with charges, smear this wall with charges, the charges on this conductor will rearrange themselves such that The electric field inside here would be 0.
So if you had an insulator instead, what would happen to charges?
The insulator, the electric field goes through the insulator.
Okay.
So if you had a plastic sphere, electric field. So let's say again, in this room there was the electric field, and you go get a styrofoam sphere and put it like that. That would be the electric field. Okay. If you take here's a copper object, and if you take and go into the store and buy a bunch of charges and put it on the copper surface, they'll all lie on the surface. None of them will be inside. And they'll distribute themselves so that the electric field inside is 0. That is their goal. Okay? Because if you had any electric field inside a metal surface, so let's say if there was a non-zero electric field, what will happen? The electrons will move in this direction. They'll arrange themselves so that, and positive charges will move in this direction, and they will cancel this electric field. So on a conductor, all the charges will rearrange themselves and such that the electric field is 0. So all charges on the conductor in electrostatic equilibrium reside on the outer surface. Okay, this is an electrostatic equilibrium. Now, when you connect batteries, we'll learn this later. So here's a conductor, a copper rod. When you connect a battery there, this will introduce an electric field inside the conductor, which will drive a current. Okay. So this is not a static equilibrium condition. Okay. So this is dynamic equilibrium. Okay. So in electrostatic equilibrium, electric field inside a conductor is 0. Okay. No charges reside on the surface. So if you have any extra charges, they'll be on the surface such that they make the electric field 0. And if you put a bunch of extra charges here, if there's a cavity, there won't be any charges on this surface. Okay. What is this showing you? Again, what is the electric field needed for a spark to occur? Yep, so the electric field needed is 3 million volt per meter or newtons per coulomb. Okay, so here the field is created strong enough where you're getting sparking. So this is lightning. Would you want to be here? No? Okay. That strong field, lightning will go through you to the ground. But look at this. If you're inside a metal cage, this metal cage shields you from all the electric field, external electric field. Okay, so what is going on? So let's show you what's going on. Okay, let's say there's a very strong electric. Oops. Let me draw the metal cage first. And I'll do a simple rectangular metal box. Okay. And then let's flip a switch and turn on an electric field that is 3 million volt per meter. What will happen is, okay, so as soon as you have an electric field like that through the metal, okay, what will happen? All the electrons will move here, and the electrons will collect over here. There will be positive charges, so this becomes positive. And this will create its own electric field in this direction, which is equal to 3 million volt per meter. And so this electric field will cancel that. And so inside the cage, the electric field will be zero instantly. And so you are shielded from this external electric field. Okay? So that's why this person is not worried. Okay.
You still wouldn't want to touch the metal with your hand, would you?
You can touch it from the inside.
From the inside, you would
Yeah.
be able to?
Yep. I got to be in one of these last summer. Let's see if I can find a picture.
And that's because the process of it transferring is so fast that when you touch it from the inside, it doesn't go all the way
Okay. So where does the charge reside on this
to the
thing?
surface.
On the outer surface.
Okay. That makes sense.
Okay. So that's called a Faraday's cage. And your car is a metal cage, at least the old cars. I don't know about the new cars, so during a lightning storm, the safest place is being inside a metal cage. Okay. So now, if you have a charge inside, then you would have electric fields inside this hollow. Okay. Okay, but again, the charges, so if this is 1E, these charges will rearrange themselves so that all the charges are, the electric field inside the metal is zero, okay? So let's say this is 10E, then they'll arrange themselves. So the center of these positive charges is right on top of there to make sure that the electric field inside is zero, okay? And you'll have a bunch of negative charges. Okay, so here's what this is showing you. Here's a metal shell. Let's say you put in a negative charge in here. What needs to happen is all the charges need to rearrange themselves so that the electric field here is zero. Okay, so when this is negative, you'll get a bunch of positive charges rearrange themselves, such that the center of this positive charge is right on top of there. And then you get a whole bunch of negative charges. The sum of these negative charges is equal to that. The sum of these positive charges is equal to that. Okay? That's how the charges will rearrange. And that happens instantly. Okay, you saw that if you have a conductor and you put a bunch of charges, they all go on the surface. And the electric field close to the surface is given by sigma, the surface charge density, divided by epsilon naught. Now, how do the charges arrange themselves on a conductor? On a conductor, the charges are free to move about. What does this guy want to do? He wants to be as far away from him as possible. So on the surface, they'll spread such that they're as far apart from each other as possible. But let's come to a sharp corner. This guy cannot fly away from him. There's no room. You'd have to go outside the metal. So near sharp corners, the density is large. The electric field here is much larger than here.
So they tend to go outwards rather than move towards the center.
No, well,
Oh, I see.
mhm. So if you put a whole bunch of charges on this surface, here they can be far away from each other, but here they cannot. So surface charge density is higher there. So here's see, the electric field is much higher than, and here is higher than here. Okay, to start lightning, you need an electric field of 3 times 10 to the 6 newtons per coulomb. So lightning is going to start here rather than here.
Which is why lightning gets attracted to the
Yeah.
little spiky.
Yep, so when you build a house, you don't want lightning striking your house, so what you do is you put a spiky metal and conduct that to the ground. Okay. So lightning will hit this and all the charge will be conducted to the ground. All right, we'll just introduce one concept for you guys, just so you know this thing. Okay. You guys know, well, so this is an angle. Do you guys know how radians, the angle is defined in radians? It is the arc length divided by the radius gives you the angle in radians. Okay? So for instance, how many radians to a full circle? 2 pi. The arc length for a full circle is the circumference. 2 pi r divided by r gives you 2 pi radians. Okay. Now we can generalize this concept. Okay. So if you have the surface of a sphere, okay, now we can define a solid angle. Okay. A solid angle is measured in steradians. Just like a one-dimensional angle was in radians. And the way we define, just like in this case, arc length divided by the radius will define a steradian as this area divided by r squared. Okay, these guys are dimensionless quantities, so it's this area divided by r squared. Well, how many steradians for a full sphere? The surface area of your sphere is 4 pi r squared divided by r squared. 4 pi steradians. Okay, so the solid angle at the center of a sphere is 4 pi. Okay. Similarly, you can generalize it to higher dimensions. Okay, so you can generalize. So this was a two-dimensional surface embedded in 3 dimensions. You can embed a 3-dimensional surface in 4 dimensions, and so on. So, all right, guys. So